Welcome to this lecture of numerical analysis. In this lecture, we will study the Newton's formula of interpolation based on the forward differences as well as based on the backward differences. But before doing the Newton's formula of interpolation, we will explain why do we require the forward and the backward differences and what are the kinds of the problems for which we need to solve. We need to use these differences. Assume that we are given a table of values xi, yi, I ranging from 1 to n of the function y equal to f of x, and here this function y equal to f of x will not be known explicitly, and here we have a condition that the values of x are equally spaced. That means the point is x1, x2, xn, they form an arithmetic progression. So we are given here the points like this. We are given the points x1, x2, so on, xn, and the functional values are these points which are y1, y2, so on, yn, and defined in this way that f of x1 is y1, f of x2 is y2, f of xn is yn. Now these points x1, x2, xn, they are equally spaced. That means the points x1, x2, xn, they form an arithmetic progression. So we have the conditions here that we have an unknown function y equal to f of x whose set of values is given here x1, x2, xn, and their functional values y1, y2, yn, and these xi's are equally spaced. Now suppose we are required to recover the values of f of x for some intermediate value of x. Now suppose that these xi's, they are defined on an interval a b, where the function f is defined as f is divided from on the interval a b to some set of real numbers. Then we are given only n functional values at some n indicated points of this interval a b, and we are required to find the intermediate. We are given some intermediate value of x belonging to this interval a b, but not among these points x1, x2, xn, and we are required to find the functional value of f at that point. Or if we are required to find the derivative of f at any of the points of the interval a b, then the methods used for solving these kinds of problems, they are based on the differences which we will now proceed to define. So we have two types of differences here. Two types of difference here. One is the forward differences and second is the backward differences. Now we now proceed to define both of these types of differences. How do we begin the forward differences? Given a set of n plus 1 points, so if y0, y1, so on, yn denote a set of values of y, denote a set of values of phi, then we have the differences like y1 minus y0, y2 minus y1, so on, yn minus yn minus 1. These are the differences of phi, are the differences of phi. Now denoting these differences by delta y0, which is defined as now y1 minus y0, the first difference, the second delta y1, which is defined as y2 minus y1, and so on, and the last difference is delta yn minus 1, which is now defined as yn minus 1. So if we denote these differences defined above in this way, then this delta is called the forward difference operator. Forward difference operator. Now we can also define the differences of these forward difference operators. So actually now we have a new list of pointers that we can denote like first we have delta y0, then we have delta y1, and so on, delta yn minus 1. So these will also be some real numbers. Now if we define the differences of these differences, then they will be called the second forward differences. The differences of now the differences of first forward differences. The differences of the first forward differences are called the second forward differences. They are called the second forward differences and defined as, or we shall do before I denoted by, which are denoted by. Now second forward difference will be denoted by del square of y0, now del square of y1, so on, del square of y n minus 2 and define it as in this way. Now first we have this del square of y naught, so this will be equal to del y1 minus del y naught. So here from we need to understand it properly. We have defined the first difference as delta y naught is y1 minus y naught. Now delta square y naught is delta y1 minus delta y naught, so they are in same alignment. So the second forward difference can obviously obtained by multiplying this first forward difference by delta on both sides. So delta square y naught is delta y1 minus delta y naught. But now here we can use the values of y1 and delta y1 and delta y naught. Now delta y1, as we know, that is equal to y2 minus y1, then delta y naught, that is y1 minus y naught. Now taking this sum, we get y2 minus twice y1 minus y naught. So this is the value of second forward difference for this delta naught. So this is now similarly delta square y1. We can define this as delta y2 minus delta y1. Now delta y2 is equal to y3 minus y2, and delta y1, that is y2 minus y1. Now this becomes y3 minus 2y2 minus 2y2 minus y1. Similarly, when we arrive at some rth stage, so this delta square of y, suppose r, this will be equal to delta of y r plus 1 minus delta yr, and the answer for this one will be delta, sorry, not delta, it will be y r plus 2 minus twice y r plus 1 minus y r. So that's how this second forward difference operator behaves. Now similarly, we can now define the differences of the second forward differences, and they will be called the third forward differences. So similarly, in this way, we can define the forward differences of kth order by they will be denoted by like this, delta ky naught, which will now be defined as, anyway we don't need to write the definition, so this will be delta ky naught, then this we will have delta k y1 and so on. And now the kth forward difference can be defined up to yn minus k. As we can see here, the first forward difference is up to delta yn minus 1. So here we have the power 1. If we add this n minus 1 plus 1, we will get n. Similarly, in the second forward difference, this n minus 2 plus 2, that's n. So therefore the kth forward difference, n minus k plus k, that will be equal to n. So the kth forward difference can be calculated by these things. So these are the forward differences of these values. Now in a similar way, we can define the backward differences. Now let's proceed to define backward differences. Backward differences. Okay, now we again have the same set of values. So we have already defined the differences, y1 minus y naught above, then y2 minus y1, then yn minus 1. These are the differences. So they are the same differences that were defined here, y1 minus y naught, y2 minus y1, and so on. Now denoting these differences by now we will denote this, the first difference, by delta y1, which is equal to y1 minus y naught. Similarly, now delta y2, which is equal to y2 minus y1, and so on. And the last difference is delta yn, which is equal to yn minus 1. Then this delta is called the first backward difference operator. Is called the backward difference operator. This is called the backward difference operator. Now, and similarly, we can define the second backward differences and third backward differences. So we will not now write too many details, the differences, or we can write down the second forward differences or the second backward differences are defined as so this will be now delta square of y2, then delta square y3, so on up to delta square yn, and defined as then so that where this delta square of y2, now this will be equal to delta y2 minus delta y1, which is equal to, now delta y2 as we know, this is equal to y2 minus y1, and delta y1, that is y1 minus y0, so this will give us y2 minus twice y1 minus y0. And similarly delta square of y3, this is equal to delta y3 minus delta y2. Now delta y3 is y3 minus y2 minus delta y2 is y2 minus y1. Now this will be equal to y3 minus twice y2 minus y1. Now here we will try to make comparisons, and similarly and so on. We will try to make the comparisons. Now the second forward difference delta square y0, the value was y2 minus 2y1 plus y minus y0, and we have the same value here, y2 minus 2y1 minus y0. So therefore we have like this observation, we have this delta square of y0, this is same as delta square of y2. So that was the first second forward difference, and this was the second backward difference. Similarly, if we have this delta square of y1, this will be same as delta square of y3. And back forward difference of the third one, that is delta square of y2, this will be same as the backward difference of y4. So therefore all these values will be equal. So this is how do we define the forward and the backward differences. Now we can now let's take up one exercise. So find all possible forward and backward differences for the following data. And the data is like this. We will write x here and the functional value is y in the second row. So suppose that x is equal to 1 and y is equal to 24, x is equal to 3, y is equal to 120, x equal to 5, y equal to suppose 336, x equal to 7, y equal to 720. We will find the all possible forward and the backward differences. By all possible we mean we will first find the first forward difference and second forward difference and so on, and see what will be the highest order forward differences that we can compute. Okay, solution for this thing, we will just form a table, forward difference table, forward differences table, and we will form the table like this. So first we write the values of x here, which are 1, 3, 5 and 7, and we can clearly observe 1, 3, 5, 7, they are equally spaced and they are spaced by a step length of 2. Now here we will write down the values of y that are given. Now that is 24, 120, 336 and 720. Now we write down the first forward differences, with the column shall be denoted by delta. Now the first forward difference is delta y0, which is equal to y1 minus y0. Now here we have, so we can denote this is our value for y0, this is our value for y1, this is our value for y2, and this is our value for y3. So therefore we have this delta y0, this is equal to y1 minus y0, that is 120 minus 24, that will be equal to 96. And similarly delta y1, or we shall write it in this way. So this is our y3, y2 and y3. Now delta y0, which we have y1 minus y0, which is equal to 96. This is difference of 120 minus 24, so we try to write it in the middle of these two. rows. Now similarly delta y1, this will be equal to y2 minus y1. So this will be 336 minus 120, that is equal to 216. So that is in the middle of the second and third row. Now delta y2, that is equal to y3 minus y2, and the difference of 720 and 336, that is 384. So this is our second table, first forward difference. And now the second forward difference is the column shall be denoted by delta square. Now first of all, delta square of y0, that will be equal to delta y1 minus delta y0. So it will be the difference of 216 and 96. Now taking the difference, we get 120. And similarly here, delta square of y1, which is equal to delta y2 minus delta y1, that is 168. Now we can also define delta cube. This will be equal to delta cube of y0. Now this will be equal to 168 minus 120, that is equal to 48. Now since we have obtained just one point in the third forward differences, now once we obtain the only one point, therefore we cannot define further differences of higher orders. So we can define the forward difference of orders 1, 2 and 3 only. Now similarly the backward difference table. Backward difference table. Now we will form the table in a similar way. X now we have y, x is 1, 3, 5, 7 and y is equal to 24, 120, 336 and 720. Now the backward difference table, this will be again the same as y1 minus y0. So this table, this value will again be equal to 96. And here we will again get 336 minus 120, that's 216, 720 minus 336, that is 384. And now the second backward difference is, it is 216 minus 96, that is equal to 120. And now second forward backward difference of these two numbers is 384 minus 216, that is 168. And the third backward difference is 168 minus 120, that is 48. Now we can compare these two tables. Actually they will give us the same set of values, so we will have the tables in a similar way. Now we can move forward, and now we are ready to define the Newton's formula for interpolation. Okay, this is Newton's formula for interpolation. So we will actually have two Newton's formula, one based on the backward differences and one based on the forward differences. So now let x0, y0, x1, y1, so on, xn, yn be given. It is required to find a polynomial which we shall denote by yn of x that agrees with the set of tabulated values. So that is actually our problem. We will be given just n plus 1 points, x0, y0 to xn, yn. We will here find out a polynomial yn of x that will satisfy all these points. Then using that polynomial, we can find the value of any intermediate value of x or its derivative. Okay, so let, as we must have these points xi's to be equally spaced, we define let xi's be equally spaced by a quantity h. So define a variable x which is defined now as x0 plus p times h. So p is greater than or equal to 1. So if p is equal to 1, then we will get x0 plus h, that will be the value of x1 and so on. Then Newton's forward difference interpolation is given by then Newton's forward differences interpolation formula is given by or defined as yn of x is equal to y naught plus p delta y naught plus p into p minus 1 divided by 2 factorial delta square of y naught plus so on plus p into p minus 1 into p minus 2 so on up to p minus n minus 1 whole divided by n factorial delta power n of y naught. So that is the Newton's forward difference interpolation formula. Now before taking the Newton's backward difference interpolation formula, we will take up an exercise. So we will have an exercise here. So find the polynomial which takes the values like y of 1 equal to 24, y of 3 equal to 120, y of 5 is equal to 336, and y of 7 is equal to 720. Hence find the value of y of 2. So therefore we have a problem for Newton's interpolation formula, and we will use the forward differences. Okay, so our solution is we will form the first forward difference table. So our first step will be the forward difference table is the forward differences table is. So as we have already discussed the forward difference table for the same set of values 1, 3, 5, 7, then values of y are 24, 120, 336 and 720. Now values of delta are 96, 216, 384. Values of delta square are 120 and 168. Values of delta cube, that is 48. So we have forward, this is our first forward difference table. Now here these xi's differ by 2, hence our h is equal to 2 here. Now in the definition, so hence we have x, that is equal to x naught plus ph, gives, that is we have x, now x naught is equal to 1 plus 2h, which gives, sorry, not 2h, is 2p, which gives, because x naught is equal to 1 and h is equal to 2, which gives p is equal to x minus 1 by 2, x minus 1 divided by 2. So this will be our first step to evaluate the value of p using the given information. So hence now we can substitute the values in the Newton's interpolation formula. So therefore now y of x. So now let's see how many points are given. Now in the Newton's interpolation formula, if we are given n plus 1 pointers, then we write the polynomial as yn of x. So for n plus 1 points, we write n of x. Now here we are given 4 pointers, which we can call as like x0, x1, x2, and x3. That means we will get a cubic polynomial. So we can call this y3 of x. So our y3 of x will be equal to, first of all, y0 plus p delta y0 plus p delta y0 plus p into p minus 1 divided by 2 factorial delta square of y0, then plus p into p minus 1 into p minus 2 divided by 3 factorial delta cube y naught. And our Newton's interpolation formula goes up to delta power n if we are given the points from x0 to xn. So yn goes from y0 to y delta n. So now we can just substitute the values of y0, p, and these delta powers. Now y0 is equal to 24. Now p, as we have calculated, that's x minus 1 divided by 2, and delta y0, that is equal to 96. Plus p into p minus 1, so it's x minus 1 by 2 into x minus 1 by 2 minus 1, whole divided by 2 factorial into delta square y0, that's 120. Then plus similarly p, that is x minus 1 by 2 into p minus 1, x minus 1 by 2 minus 1 into p minus 2, x minus 1 by 2 minus 2, whole divided by 3 factorial into delta cube y0, and delta cube y0 is 48. Now here we can notice that we have used the values, like we have used the values 24, 96, 120 and 48 only. But in order to evaluate these values, we have to compute all the values below them also. Now multiplying all these numbers and taking the final sum, we arrive at the answer like x cube plus 6x square plus 11x plus 6. So this is the polynomial that satisfies these all points. Now in order to verify whether we have properly computed it or not, and we have not made any mistake, we will try to verify these points. Let's compute y of 1 here. So this is our y3 of x. So let's compute in order to verify verification, or we shall check it. That's not necessary. Let's compute y3 of 1. That's equal to 1 plus 6 plus 11 plus 6, which is equal to 24. Now let's see what we were given. We were given x not equal to 1 and y not equal to 24. So that's the correct value. Similarly, we can verify it for the other values. And now we are asked to calculate y of 2. Hence, y of 2 is equal to 2 cube plus 6 into 2 square plus 11 into 2 plus 6. And this total is to 60. Now we can see we were not given y of 2 here, we were given y of 1 and y of 3, y5 and y7. Now we can easily calculate y of 2 and anything. And also suppose we are asked to find y dash of 2. Now y dash of 2 will be equal to, this is equal to 3x square plus 12x plus 11. And we have to compute this at x equal to 2. So which is equal to 3 into 2 square plus 12 into 2 plus 11. Now that is equal to 9 into 3, 4 into 3, that is 12 plus 24 plus 11, that is equal to 47. So therefore that's how we use the Newton's interpolation formula using the forward differences. Now let's go and define the Newton's backward interpolation formula. So we have Newton's interpolation formula. Newton's interpolation formula using backward differences. Using backward differences. We have a simpler formula, and that can easily be used in a similar way that we have used the forward difference formula. Now this is with, again, x equal to, now xn plus ph. So this is a difference in the Newton's forward difference interpolation formula. We have defined x as x naught plus ph, but now here we define it as xn plus ph. That means last value of x plus ph. Then Newton's backward interpolation formula is given by interpolation formula is given by, now this is denoted again by yn of x. Now this is equal to, first we start with yn, then plus p delta yn, which is the backward difference operator. Now this, let's keep on comparing it with the Newton's forward difference formula. We had y naught here and p delta y naught But now here we have yn plus p delta yn. So this starts from the last values. Then plus the next term in Newton's forward interpolation formula was p into p minus 1 by 2 factorial. But in the backward difference formula we have p into p plus 1 divided by 2 factorial delta square of yn. Then plus similarly p into p plus 1 into p plus 2 whole divided by 3 factorial, then delta cube yn. Then plus so on, and the last one will be p into p plus 1 into p plus 2 so on, then p plus n minus 1 whole divided by n factorial, and this will be equal to delta n of yn. So this is how we define the Newton's backward interpolation formula. Then using the previous question again. Okay, so question solve for y 3 of x from the data y of 1 equal to 24, y of 3 equal to 120, y of 5 equal to 336, y of 7 equal to 720. So we will find the value of y3 of x using the backward difference interpolation formula by Newton. So by solution, so we have the backward difference table is given by backward differences table is, and we have already computed it above. Now we will quickly make a review of that one. So this x, y, 1, 3, 5, 7, the values are 24, 120. So values are 24, 120, 336 and 720. Now the backward difference operator, this is 96, 216, 384. Now here we have the second backward difference is 120 and 168, and the third backward difference is again 48. Now the Newton's formula will be now, so therefore y3 of x, this is equal to y3 plus p delta y3 plus p into p plus 1 divided by 2 factorial delta square y3, then plus p into p plus 1 into p plus 2 divided by 3 factorial delta cube y3. Now we just need to compute the value of yp y x is equal to xn plus ph, or x is equal to xn, so is equal to x3 plus ph, x3 plus p is same as p, and h is equal to 2, so this is equal to 2p, or we get x is equal to now x3 is equal to 7 here, as we have this is equal to x0, x1, x2, x3, so that is equal to 7 plus 2p, so that is p is equal to x minus 7 divided by 2. Now using this value of p here in this equation, and this delta y3 is equal to 720, so this is the value for delta y3, so this is our delta y3, this is the value for delta square y3, this is equal to delta cube y3, so this is okay, so this is our delta cube y3, this is delta square y3, and this is delta y3, and this is simply y3. So using these values here in this equation and the value of p, we again arrive at the equation then y3 of x. This will again be the same polynomial x cube plus 6x squared plus 11x plus 6, which was also obtained in the Newton's forward difference interpolation formula. So this is where we conclude this lecture.